Hello everyone, welcome to Lecture 1 of the next unit, Kinematics in 2D. And in this lecture we're largely going to be expanding on things that we saw in Lecture 3 of the Vectors unit. So here I am with a mass on a spring. And you'll study the motion of a mass on a spring in great detail in Phys 1201. But for me right now it's just a convenient motion because it's a motion in a straight line. Now what I want you to think about is what happens when you couple that motion of the mass on the spring with me walking to the left at a constant velocity. And you see I've done video analysis to introduce a motion diagram with the points that the mass is sitting at. So here is a still picture of that whole motion diagram, and I've just added two velocity vectors down here. And the reason I've done that is that it's going to allow me to use vector subtraction to find the acceleration at that point. So there we go, there are the two vectors, and as usual I need to flip VI, and when I do that you see that this motion has an acceleration which is straight up at that point. And it might surprise you, given that I was walking to the left, that the acceleration here is straight up. Let's talk about adding apples and oranges. So I have 4 apples and 3 oranges, and so I'm going to write fruit me is 4 apples and 3 oranges. And you have 2 apples and 6 oranges, so I'm going to write fruit you is 2 apples and 6 oranges. And so our total fruit supply is just 4 apples and 3 oranges, and 2 apples and 6 oranges. And so that is just 4 plus 2 apples and 3 plus 6 oranges. Okay, so I mean, I'm sure in grade 1 you could have done this. Maybe not with the A's and O's in the equations. The point is that if we change my number of apples, it only has an influence on the number of apples in the final answer. Obviously, it'll have no influence on the number of oranges. So the way we add the apples and oranges here are totally independent of each other. Well, this is a physics course, not a grocery store inventory management course, and so unsurprisingly, I'm not really interested in adding apples and oranges, but the point here is that it works exactly the same as adding vectors. So when you have a vector and it has its x and y components, and you have another vector and it has its x and y components, then the way you add them is just like adding apples and oranges, in that all of the x components add to each other, and all of the y components add to each other. And we saw this in the last unit. But the point is, now this means that the way that an object is behaving, say vertically, is frequently independent of the way it's behaving horizontally. And understanding this can save you a lot of trouble when thinking about two-dimensional motions. So having thought about apples and oranges, and then how that's just like vector addition, we can now perhaps explain why this acceleration vector here is straight up, perhaps counterintuitively to you, because the fact that I'm walking to the left is irrelevant here. the spring is making the mass accelerate up. And because I'm walking at a constant velocity, the horizontal component of the acceleration vector is 0. So the acceleration is straight up, as we see in the motion diagram. Here's this motion diagram again from the last unit. And let's just think about going from some time that I've called initial here to some other time final here, and what the average velocity and average acceleration would be over that much longer time interval. Well, as usual, v_av is just going to be a displacement. So there's the displacement over the time interval, which is just going to give us some other vector in the same direction as the displacement. So remember that the size I'm drawing this vector is not really very important, but the direction is. It's in that direction. And I'm just going to get you to recognize that this is actually sort of the same as something you know. You know that for just a bunch of numbers, to get an average, you would add up all the numbers and divide by the number of numbers you have. Now look at what's going on here. If you add up all of these velocity vectors, well, they're all head to tail. And so you get a vector that looks like this. That's the vector addition. And now if you just divide by the number of vectors, you're going to get some smaller vector here. And so even though this is a definition that's quite different from how you may usually think about an average, it in fact comes out to the same thing. Now let's just think about an average acceleration. And so I'm going to take this vector here just after the I as my initial velocity, and I'm going to take this velocity here just after the F as my final, and I'm just going to drag them over here where I can work with them. And as usual, we need to take our initial velocity and flip it end for end if we're going to do a subtraction. So there it is, flipped end for end. And I'll just snug it up over here. And now we can see that delta V looks like this. And so the average acceleration points in this direction. So remember that these green velocity vectors that I've drawn on this motion diagram are average velocity vectors, right? So for example, this is an average from this point to this point. The actual path that this object follows would be some curve like this. And wherever you look, the instantaneous velocity would always be a tangent to the curve, like so. But now remember that if this is a v instantaneous, and I've deliberately drawn it at a point roughly halfway between these 2 points, and notice it's in about the same direction as this average velocity. So this average velocity is a good approximation of the instantaneous velocity at the instant halfway between those 2 points. In the lab, you're often going to calculate accelerations from data. And it's easy to lose sight of what it is you're doing because you're often just working from columns of numbers. So let's do it from a motion diagram so that we can picture what's going on. And let me start off by getting the acceleration at 0.4 seconds. Now, in fact, I can't do that exactly because I don't know a velocity at any instant. All I know are these average velocities. So we know, though, that I can approximate the velocity at 0.3 seconds, right, halfway through this time interval, as this displacement, so that's 2 meters, but be careful, that's 2 meters in the x direction over the time interval, right? 0.4 seconds minus 0.2 seconds. So that's 2 meters over 0.2 seconds, that's 10 meters per second in the positive x direction. And similarly, I can say v at 0.5 seconds is now from this displacement vector, so 3 meters in the positive x direction, over, again, that's going to come out to 0.2 seconds. And so that's going to be 15 meters per second in the positive I direction, or in the positive x direction. And so now I can get my acceleration by the difference, the delta v, so that's going to be vf, 15 meters per second, I hat, minus my vi, 10 meters per second, I hat, over, and be careful with the delta t. Remember, we're working with approximations to the velocities at 0.5 and 0.3. And so that is going to be 5 meters per second over 0.2, so that is 25 meters per second squared in the positive x direction. And notice that it gave us the expected result. This is speeding up. It's given us an acceleration pointing in the direction of motion. Let me now do at 1 second. So if you look at that, you're going to have a v at 0.9 seconds, which is approximately this v. So look at that. That is 2 meters I hat plus 3 meters in the positive y direction, all divided by, again, a delta t, which is 1 minus 0.8 seconds, so 0.2 seconds. Okay, and so that is going to be 10 meters per second in the x direction and 15 meters per second in the y direction. And if you look at that v at 1.1 seconds, halfway through this time interval, hopefully you can convince yourself that it is just 10 meters per second. I'll leave you to calculate this in the positive y direction. And so that gives me my acceleration. I need to take vf, 10 meters per second, in the positive y direction, and I have to subtract my vi, 10 meters per second, in the x direction, and 15 meters per second in the y direction, and I have to divide that all by 0.2 seconds. And so I'm going to get negative 10 over 0.2 is 50 meters per second squared in the x direction, and negative 25 meters per second squared in the positive y direction. And just notice that it has a negative x component and a negative y component, and its x component is bigger. So it's a vector that points back left and down, but more left than down. It's going to be roughly like that. And we've seen that, right? This is going around a corner and slowing down, and so the acceleration vector ought to point in towards the middle and back, and indeed that's what we've found. So here's a video of me throwing a ball, and I've used video analysis software to have it generate a motion diagram. So you can see the points. Let's see that again. And here it is with all the points shown. There's the ball, and I've inserted velocity vectors on it. And what I want you to think about is which of these gives you the correct acceleration vectors for this motion. If you're in my course and you're doing this from the Moodle site, then before you go on to the next lecture, it's going to ask you to answer this question. If you're just doing this out on YouTube, then I would encourage you to write down your answer right now before you go on to the next video.